Okay, so what we did in the previous lecture, we finished at the point where we had basically the eigenvalues and eigenvectors of the position operator. Okay, naturally we'll move on to momentum operator. And after we'll define the momentum operator and its eigenvalues and eigenfunctions, we will go and look into this uncertainty principle. Basically commutation relations and what do they tell us about what can and cannot be measured. Okay, so as we have seen in the previous lectures, the momentum operator in general is three-dimensional, therefore it's a vector, but we could also look on any component by itself. Okay, now we have to solve the eigenfunction equation and eigenvalues. That's basically the procedure that we'll do again and again and again for any physical quantities that we're interested in. So, let's start from a single component. Just simply the eigenvalue, eigenvector and eigenvalue. Equation.
It's easy to see that it needs to be a complex exponential, right?
Right.
Because of the derivative.
Once you define the operator, you define the eigenvectors and the eigenvalues. The only problem that can come out is mathematical. Perhaps you don't know to guess, but or to solve the equation. But to write down the equation and to jump to conclusions is almost immediate. Okay, so let's explicitly write down why? Because if we'll just plug it into here, we get on the left-hand side I times minus I is 1. H bar divided by H bar is 1. And therefore we just get here Px times the function. So it's definitely a solution. It's just a differential equation. If it's a discrete operator, meaning we're writing it down for a discrete values, meaning it could be a matrix, we'll solve a matrix equation. If it's continuous, it has to be differential.
Why you add this C in front of it?
Because, first of all, because I can. It continues to be correct even if I multiply it by any scalar. And second, and more importantly, I need normalization. And I'll return to it because as for the position operator, we're in a problem. See how we get out. Okay, so what happens if we are doing it for the full vector? So I have to solve I'm doing it once because, first of all, because people tend to somehow misinterpret what's done here, although it's straightforward. Second, it will return again and again and again. Let's say the course in condensed matter appears a lot.
Why psi px? Just
P.
like
Sorry. Okay, I'll write, as I say, I'm going into details that are straightforward, but I want once to clean it up as it should be written. So all I did is write down explicitly what appears in shorthand here. You can immediately see that this component has to be equal to this component because it's only part of the component that has any contribution in the x direction, the same for the y, the same for the z, and we basically solved it here. So the solution if I multiply, and for each component it doesn't matter because you don't perform any operation on the y and z here, the x and z here, and so forth. Okay, shorthand for this is writing it this form. So this will give me px times x plus py y plus pz z. Now, unfortunately, a lot of times I see students in exams writing it down, forgetting about the dot, going home happy. No, you have to write it explicitly.
If I just wrote P out, it's good.
No, it's not correct.
Because it could be vector A.
So when you're writing P, what do you mean by P? The absolute value, the norm. P is a vector. As long as you write components, all is well. And you'll get wrong calculations if you try to do it.
Just wrote the scalar multiplication, or would be good?
Yes. Just write it down correctly. No magic here. Okay. C here is, of course, doesn't have to be the same as C here, but since it's not defined with that. Okay. Now, many times people prefer to write down instead of P the K vector. And remember, fine, people use it, exchange between P and K at will, it doesn't matter much. Just don't be surprised if you see this form and not this form. And I'll use them interchangeably. Okay, so it's time to address the elephant in the room. What's this C? Well, C comes out of orthonormality. Okay, what do we expect to get here?
1.
If it would have been a continuous discrete operator, we would expect to get 1. Here, let's see what we'll get. I'm just writing down the definition here. Okay.
Why K tag and K?
Because I want to do orthonormality. What does it mean? For the same K, I should get 1 or the Dirac condition. We'll see it in a moment. For all the rest, we should get 0. So I want to see. It's the same integral. Well, why should I do it twice?
Thank you.
Okay.
Why there is a equal sign? No complication.
Remained from the previous. Okay, so I just wrote explicitly terms. Dx times this guy. It's only where that I have the x appearing, so I can do it separately. The same for the y, the same for the z. And what are these?
Delta function.
Delta functions up to 2 pi, as we have seen in the previous lecture. Good. Just the meaning of a delta between vectors. It's delta for one component times delta for the second component times delta for the third component, and if you have more components, so it continues. And this is almost the Dirac normalization, up to 2 pi to the power of 3. So I end up with a conclusion. In order to bring me into Dirac's orthonormality. So Again, all that we said for the position operator, the eigenvalues are out of the Hilbert space, but that we know immediately. What is the probability to be in any position of the... Or do I have them? Fortunately, I've already erased it, so I'll write it again. What is the probability of finding it anywhere in space here?
It's not the same probability.
It's the same probability everywhere. You can't normalize it. It can't be a solution to describe a physical entity, a physical particle. For people in optics, that's completely understandable. If you put out, can you put out a pure wave with a pure frequency? No, because then it will have to continue forever. The other way to look on it. So if you describe a particle in space, you'll have some combination of such solutions, which will give you a finite width in space and a finite width in momentum.
This is just not finite.
No,
In the space.
In space,
Yeah.
right? The same problems that you have for a delta function. It has to be at a point within a continuum. Same problem at the end of the day. Okay, so let's say someone gives me a wave function. And I want to express it in the eigenvectors of the momentum operator. Why? Because it's convenient, because I was requested, whatever reason. As with any other base, any wave function, including psi of r, could be described as a superposition of the basis vectors which we have written here. Meaning, okay, the only thing I have to correct here, k is continuous, so it should be an integer.
KK?
We'll try to find in a moment. Depends on psi, of course, right? Well, how do we find psi? I can multiply by an integral on the left side. These don't depend on K, on R. To confuse it with the integration variable. Okay, sorry, nothing wrong. Square. Okay. But this integration we have already seen. It's a delta function. K prime minus K or K minus K prime. So I'm left on this side with which you might know as a Fourier transform. Oh, that's K prime. Of course, let me forget about the prime on both. Okay, so the answer, I want to know what is the probability to find a particle described by a particular wave function at momentum k. Fourier transforms a wave function, square the amplitudes, and you have the probability of finding it at a given k. Okay. So basically, even if I didn't learn anything about Fourier transforms, it's a natural way to move from one basis to another. This particular case between momentum and position. Someone wants to guess how to convert a wave function given in momentum space into real space will work.
The inverse Fourier transform.
The inverse Fourier transforms is the only thing that changes to here a plus instead of a minus. That's it. So as I promised in the beginning of the course, we are starting to see how we are moving from one basis to another basis. This could be generalized, and we will generalize it. Okay, now something very important, a trick, or if you want to, basically it's a way to think about momentum which is applied throughout all of physics, including when you learn quantum field theory, you'll use it a lot there, is to stop for a moment and say, I don't like this Dirac orthogonality. I want to work with something simpler or more intuitive, and in the end of the procedure I'll transform my system to something else, to something of infinite size. And this trick is basically, again, used in a lot of applications in physics and elsewhere. So our big problem is that our space is infinite and we can't normalize it. So the solution is to look on periodic boundary condition. What does it mean? I'll write it down first of all for one dimension. And it's very easy to understand geometrically. This is the x coordinate after going for a distance L on it. I'm back to the same position. So it's a ring. For 2 dimensions, it will be a torus. That's a bit beyond my drawing. Relatives, but just think about a tire or regular.
Why? What you mention is
because I want to go here psi x y.
Psi x plus L and y plus L.
And experiment trying to draw it in 3 dimensions. Let's spare anyone. But it's the same idea. Yeah.
So a generalization would be that it's S1 times the dimension that I am working with.
Mm-hmm. Now, in parentheses, it's not within the material, but perhaps it's interesting to you. You've heard that in string theory you have 10, 11 dimensions. We live in 3. What do you do with all the other dimensions? You assume that they are very small. Meaning, in this case, if I wanted to describe a one-dimensional world, when I have 2 dimensions, I'll put here, let's say, Ly, extremely small, and I won't see it. In a moment, you'll understand what I mean by you won't see it. So, in jargon, it's compactified. Now, because you have all kinds of different ways to construct these small dimensions, you have many ways to compactify string theory. Now, in the good old days, 20 plus years ago, it was believed that one of them is unique, and that will explain everything that could be understood about our universe. Now it's understood that there's nothing unique. Basically, all of them work. That's from where you hear this strange number. Well, there are 10 to the power of 500 possible universes because you have so many ways to compactify these small dimensions. Okay, so another and more relevant to our daily life point to is now if I take L to infinity, then I'm back to an infinite system, right? Almost right. What is the difference between a line and a ring?
That the ring is bounded.
In topology, this has genus 1 and this 0. So it sounds something that interests only mathematicians. Well, you can do experiments and see actually the influence. Because, for example, how many of you heard about the Bohm-Aharonov effect? One. And basically, Bohm-Aharonov were Aharonov actually is an Israeli physicist, still active, although he's 90-something years old. Basically came up with the following idea. Again, not our material, it could be in the second course of quantum mechanics for undergraduate, depending who is giving it. Take a solenoid, the good old question from high school physics. Now, the magnetic field will stay on in the middle, right? Well, the truth is it has to close itself in the infinity, but nowhere in the area of the ring. Can the ring know that there is this magnetic field going through it? Intuitively, the answer is no, there's no field, so how can it feel it? Fortunately or unfortunately, yes, you can see it. There's several experiments that you can do that shows that you have a magnetic flux going through it. So the topology is interesting.
We don't know why.
We know exactly why. It's one of those effects of quantum mechanics that if you correctly calculate, you get it. Just no one expected it. If you want on a mathematical level, the entities that couples with the wave function is not the magnetic field, but the vector potential. And the vector potential exists everywhere. Strange, unintuitive, but confirmed experimentally. So, back to our case. Okay, and I'll look on one dimension. I have my ring and I have this condition. Okay. Solving the eigenvalue problem, which is essentially the same as the one that I solved half an hour ago. And I have here because it's finite, I don't need Dirac. I can go and do the calculation explicitly. So, okay, C squared, if you want to be more exact. No dependence on x, integral on dx, L. And all this has to be normalizable. Equal 1.
How do we get this C squared?
We have this and we have it squared. The phase falls off because it's e times ikx times e to the minus ikx.
And then we get the C squared.
We get c squared times integral dx. This is L. So c is 1 over square root of L. Okay, so my wave function is 1 over x. But I have another condition. follows the periodic boundary condition. Yeah, I just extracted this here, and I'm playing with this part. Okay, what's the condition on Kx? No. Yes, but not only. Any times that I have here 2 pi, or any multiplication of 2 pi, it's fine.
It's like a cosine.
Yes, I mean,
Goes back to, I think it's Euler's relation.
Yes. Because
Okay, so the fact that we went into periodic boundary condition turned me the momentum to something discrete. Because it's discrete, you can normalize it as usual, and all is good. So, if you want, well, writing down the wave function, if you'll take L to infinity, you'll get some nonsense here. But if you'll calculate a physical quantity, and you see L drops out, it's a much easier way to calculate using the periodic boundary condition and taking L to infinity only for the results. Usual normalization, nothing strange comes out here. What will happen to the orthogonality condition?
in which case?
For the discrete case.
It will become a Kronecker delta, right?
Exactly. Then it's a chronicle delta, not a Dirac delta. Then you're on a much firmer mathematical grounds. So you'll do it all the time. Field theory, and I'll comment a bit about it after we'll do a harmonic oscillator, which is the gateway into field theory. Okay, so we did 2 operators. Let's meet a third.
this leads us directly to the discretization of energy, right? We are in an empty space, so there is no potential, and we just have to square the...
Well, if you want to understand it intuitively, because your space is finite, doesn't matter that it's
right.
That it's has the periodic is periodic. Nevertheless, that as itself is enough to give you
right, because it's mathematically bounded.
A quantized momentum, and since I didn't say it yet, but this is a good point to put it in, since the energy you'll have here quantization of energy. And another thing that you can understand here, what happens if Lx is extremely small?
If L is small, then you have a lot of energy.
Meaning, in order to go from the zero excitation to plus minus 1, you have to have a lot of energy. And if you don't have this huge quantity of energy, you actually can't perform any experiments that will show you the extra dimension. It's there, but you're frozen in some given energy. So for you, the fact that you have a very small dimension doesn't mean anything as long as you don't do experiments on huge energies. So when they started with a Large Hadron Collider, and someone had ideas that perhaps these curled up dimensions are small but not extremely small, some people had the idea, well, we would be able to supply enough energy there to see some influence in the experiment for the fact that we have extra dimension. They didn't see anything, so you can always say, well, the dimensions are small. But this is at the end of the day the reason why extra dimensions don't necessarily change the physics that you see on everyday life in quantum mechanics, for the simple reason. In order to see an influencer, you have to go to very high energies that we don't have here. Okay, so now naturally we'll go over to speak about energy. So I have two ways to write down the energy operator. can write it down as the first derivative in time, and I can write it down as a Hamiltonian, which is also there. And our good friend, the Schrödinger equation, just equates them 1 to the other. That's the Schrödinger equation. Let's meet another old friend here. So this is the Schrödinger equation. And what did I write here?
Time independent.
It's the stationary Schrödinger equation, but now we understand that we can look on it with a different angle. This is basically the eigenvalue and eigenvector equation of the Hamiltonian operator. Okay, this already depends on the form of the Hamiltonian, so I can't give you a general solution. But we'll spend a couple, if not more, of lectures on particular systems. We'll start with one-dimensional free electron, free particle, and we'll see exactly this behavior. We'll then jump to particle in a potential in a box and in a harmonic potential, and usually we would have ended up with the hydrogen atom, which is a different kind of potential. So basically, as I told you, most of the course is solving eigenvalue and eigenvector solutions for a given operator, in this case the Hamiltonian. And as usual, if I have a wave function, I can write it down in the basis of the eigenfunctions of the energy or of the Hamiltonian. So I have here some amplitude, and this amplitude, how do I find it? No, it's not Fourier transform, because Fourier transform is for the momentum. this would be, well, you have to
operator.
tell me what are the psi is. Psi is times
Psi E, any psi?
the psi that I'm interested in. Okay, let's prove it. And it's general for any basis of any operator.
It's only to put the identity operator, right?
Let's say I have some operator A. It follows an eigenvalue, an eigenvector equation. So, I'm clever, I solved it. I can write down the whole basis of this operator. Okay? So, if you come and give me any wave function in this Hilbert space, it could be written as sum of C of A, sum over all the A's here. That is the result of these eigenvalues being a full basis of this space. Okay, now I want to find out what is C of A.
Multiplied by psi conjugate.
Well, so don't even need, I could have put here the identity, but even simpler. A prime, sorry. Forget about the prime. That's amplitude. Because the eigenvalues of the momenta were e to the power I kx, you get a Fourier transform. If you have some other function which is an eigenvalue that you recognize as a given expansion, and we will meet things like Hermite, Legendre, and all these lovely polynomials, it would be these functions. But this is a basis, and therefore this is exactly what I've written here. So you know now to move from one basis to another. Okay, commutation relation and uncertainty principle after the break.
בגלל שהעברנו את העברת האוריינטציה שלך למה דיגונים, פה איך ניחשנו, כי אנחנו לא יודעים מה הוא כאילו זה המומנטום הוא בעזר?
לא, עד כדי חלקי, אמרתי שהם מתחלפים פשוט, אם אני זוכר עושים את ה-H או לא זוכר, והסיבה שמשתמשים הרבה ב-K ולא ב-P, כי אתה לא צריך H.
צלנים, כמו שצריך.
או לחילופין להודיע שאתה עובד ביחידות שבהן H בר הוא אחד.
כן.
אני עייף.
אתה רוצה להכין לקפה אחי? אני צריך לשכוח מזה. תשמע אחי, כל הרצאה המוח שלי מתפוצץ אחי, שאני לא יודע מה. והאפקט הזה שהוא אמר עכשיו זה צורט אחי.
כן, הסדה המגנטית עלו, אבל הפוטנציאל לא.
זה מה שאמר, כן.
תשמע, זה לא רלוונטי, יש לה קורס.
כן, אבל זה משהו כנראה גם לא רלוונטי. תשמע, לך תדע מתי זה יהיה רלוונטי, אחי, תלך תפגוש את זה עוד איזה כמה שנים אחי לא יודע אחי, תעשה יסודות קוונטים מרוכבים אחי בחלל
חלל עצמו
תפגוש את זה אחי, תהיה כסף איתם
我也不知道在干嘛，好吓人。我感觉他讲课多奇怪，我也，我都不知道这个脑子痛到哪里去，就是总是发那种输液的，就是这么，就很别扭，特别奇怪，这能干啥吗？我感觉不如离异，离异好，可能对，感觉不如高中。然后显得这样自学是我听过的最舒服的。
כאילו, יש הקורסים כאילו, המסלול שלי אין לי אפשרות לקחת כאילו קורסים רק במסלול עצמו, כאילו צריך לשם את זה עוד כאילו לקחת איזשהו קורס. אבל יש לי את מודלים חישוביים.
אתה עושה עכשיו נכון? היה לכם לא חלום בזמן.
כן.
כן, חבר שלנו גם עושה. הוא עושה תואר במדמה אחת זו. דווקא את זה למינימום בתיכון. למד במודלים, לבגרות במדמה.
כמה שכאילו בבגרות נותנים לי את אותו חומר, כאילו אני...
אבל אתה לא מבין, לא באמת...
לא, אבל כאילו מה שקורה שבתיכון אתה לא עושה את ההוכחות המלאות ואת השפה.
אין לך פורמליזם כאילו, אין לך...
כאילו מה שמבקשים בתיכון זה פשוט לסרטט.
כן, בדיוק.
כאן אתה צריך לעבוד עם חמישייה סדורה בשביל אוטומט צפית מיניסטית.
כן, הוא אמר לנו שיש לך ממש כאילו נוסחה, בדיוק נוסחה, ממש דרך פורמלית כאילו לכל דבר, נגיד אתה רוצה להגיד שמשהו זה חופשי כשלא חופשי, כאילו כל שטויות האלה. אתה ישן אחי, יש לך עוד קוונטים ואז יש לך עוד מלטי 3 לשני. ואז יש לך עוד...
מה אתה רוצה? אסור לי לישון אחי?
בוא לא נשאר בתחילה אחי.
אחי, אני לא יודע, תשחרר.
אין לי כוח אחי. בוא אחי, יש דוח להכין אחי, בוא נסיים את הדוח הזה עד יום שלישי אחי. ואז אפשר ככה לעבוד הכי טוב. זה דווקא טוב שפספוס למעבדה אחת, אתה ככה יש יותר זמן אחי לכל דוח. כי אם לא, אז היית צריך להגיש ליום שלישי הבא דוח על המעבדה. זה די מעצבן אחי. באלקטרוניקה למעבדה הזאת, אני יודע, אם זה באמת מעבדת הסבר או מעבדה רגילה, נראה לי זה מעבדה רגילה של הקולטרים. אני אדפיס את כל התדריך ולכתוב על התדריך מאחורה ממש מה הנוסחאות שהוא אמר, הכל, כי נכתוב לעצמנו ישים מהלונדה אפילו, לא נסכם את הלונדה, שיהיה לבוא הדוח בכללית ממש ארוך אחי. כן, אחי, אני מאוד לא אסיים את הרקע התיאורטי, אבל אני ממש ארוך.
צריך לעשות אותו אחרי הבוחן בלופי, לא יכולים לגעת בכללית.
זה הרבה כלל של מונה של אופיס.
שישי שבת.
נראה לי אני שווה עמד על הדוח הזה, אני אנסה לעשות שיהיה כמעט... נשאר ככה לי חשוב לי אחרי. זה משחק. זה לא... יום אחד לא יספיק לך לעשות כל החישובים האלה. אם אנחנו עובדים ביחד אז כן.
לא כותבים על הדלת.
הנה תראה כתבו על הדלת. הנה זה ניט, לא? מה זה האוטו זאת? האוטו זאת רגע שלו.
זה אטה.
אטה? אטה. זטה, מי? ואיך עושים קסאי? קסאי. איך עושים קסאי?
ככה
זה...
לא. ככה וככה. זה היה לזה איזה גודל בחשמל.
תעשה רגע. ככה?
לא. אולי כן, זה קצת קטנה, אבל קסאי זה פשוט כמו X, רק שאחד הרגליים מתקטלת. כן, היה לזה גודל בחשמל.
זה לא קסאי, זה חי.
זה חי.
זה חי. קסאי זה מה שעשית בהתחלה.
תשמע, אחי, מה איזה קורס ככה? מיני קורס אחי ביוונית ככה,
יש
לדעת.
לך חצי בקיבוץ.
לדעת יוונית, אחי. יש קורס כזה? ביוונית?
כן, אני לא אעביר אותי.
שלא. תשמע, ללמוד יוונית אחי זה פסיכי. זה נשמע, זה שפה יפה.
הכתיב בגידי, בשפה בוחרת.
למה? אני מדברים...
שמעת מישהו יווני מדבר
כן.
פעם אחי?
כן,
לא, אז לא שמעת.
שיחקתי משחק שלם ביוונית אחי, ביוון, כל המשחק.
אח שלי.
כל המשחק קורה ביוון אחי. סוסים קריטות.
אוי נו, אז לא שמעת, אנשי רחוב אחי, מוכרים חלב.
אחי, אני דרך להגיד לך מטומטם אחי. מלאקה.
וואלכ, כן?
כל המשחק אחי, מלאקה.
וואי אחי, איזה עייפות ואני לא נרדם.
אחלה משחק אחי, וזה אין שם לבנות. ובנים, לא יודע מי זה, הכל, לא יודע. אתה יכול פשוט לעשות מה שבא לך.
תביא איזה בייגל, יש לנו שפה?
לא, אני שכנו. תשמע, סטרפסיס אחי, זה כמו אלוהים.
יש בזה קפאים?
לא אחי, יש בזה דבש. סתם, רוצה להשאיר אותך ערב, זה קצת כזה מעקצץ.
הנה קסאי.
נו, זה... חבול. קאפה זה פשוט...
איזה יפות!
מנואל עשה קאפה.
וואי, אנחנו ממש לא מכירים הכל. טאו.
לא, יש חלק
יו
שאתה יודע...
פסילון, אחי. יו פסילון, איזה פסיכי.
יש חלק שאתה יודע קטן, יש חלק שאתה יודע גדול. מה זה טאו גדול? אתה לא יודע.
טאו גדול זה טי. רוב האותיות הגדולות ביוונית הן מאוד דומות לאותיות באנגלית. יש יו פסילון, אחי, זה די פסיכי. זה כל הגריס אלפאבית?
גריק, לא גריס.
גריס.
גריק.
גריס זה יוון.
כן. גריק זה יוון.
מה אתה עושה?
אחי, אני מנסה להשאיר את התמונות, אחי.
הנה אתו.
אטה זה אין כזאת. ברגל ארוכה.
מה? אומיקרון, אחי.
אוקיי.
יש עוד שקוראים אומיקרון.
נו, היה נגיד קורונה כזה.
אחי, סי, רו.
אני מכיר את האותיות ביוונית.
כן. ניו, זטה.
רק יופסילון שלך, פשוט.
אלפא, בטא, גמא, דלתא, אפסילון, זטה. אטא, תטא. יש לוטה. לוטה. מה זה? זה כמו אל.
לוטה,
זה לגרנג'יאן, אפשר לדבר.
נראה לי לא, זה לא נראה כמו גרנג'יאן.
אחי, אני לא אוהב את הקורס, אחי.
אין שום לוטה.
אתה מתרגם גם מרצה.
איפה אתה רואה לוטה?
אולי זאתה, אחי.
סטיגמה, הטה, סן. זה אותיות שלא בשימוש. פרופ,
אסור לי אמור.
אותיות בסימוש
תראה, יש לך קולות, אחי.
אין פה לא.
זה לפי סדר, אחי, תראה.
אלפא וגם פה אלפא בטא, גם בטא, אפסילון,
אחרי
יוטה,
אחרי
פאפה,
תטא.
למדה,
לא, זה לא לפי הסדר, אחי.
או סיגמה טאו.
אחי, זה לא לפי הסדר אצלך. תראה, זה לא לפי הסדר.
מישהו רוצה, בא לו לנקות את הלוח עם זה, זה ינקה ממש טוב. קיבלתם את המייל?
כן, כן, תודה רבה.
אם אתם רוצים,
אני מוחק לו את זה?
גיליון ציונים שלכם מהענבר.
כן.
לסגור ממש את הפינה, יראו שעשיתם.
כן, כן, כן. כתבתי לה, עשיתי לה, זה אם היא תבקש יותר נשלח לה.
אחלה, יופי.
תודה רבה.
כן.
אחי, לנקות לו אבל? למחוק לו כאילו הכל? אתה בטוח שלא צריך את זה יותר?
מקסימום נאשים אותו.
אני לא רוצה שתאשים אותי.
קבל 4 בקרים.
טוב, זהו בטוח לא צריך.
לא, אבל אתה תקליט טוב.
כן, אחי, צודקת.
ידעת מה היא עושה, לא?
איך קראת לה?
אורטל קוראים.
קוראים לה נירית.
נירית?
זה נירית, אחי, זה האישה שאחראית על האקדמיה בתיכון.
באמת? לא יודע, חיפשתי לא מצחיק לו.
אחי, תקשיבי למקסים, מקסים יודע.
בסדר, אני הסתכלתי בוויקיפדיה, לא חשוב, אני לא מזל.
מה, ויקיפדיה יודע?
זה יוטה. אתה רואה כן ויקיפדיה יודע.
מה, זה יוטה? זה לא יוטה? להחליף יד. כן, אני מרגיש רע, אחי, אם הוא צריך את זה. כן, אחי, זה לא זכה שני בינה? זה אמור לעשות לך כזה אפקט משחרר בפה. נגיד, המציצה, אחי. זה למציצה, לא גסת בזה, נכון? זה בסדר שמחקתי? כן, היא הביאה, היא אמרה תמחק זה... כי הלוח היה ממש מלוכלך.
הוא בקראטה קיד שהוא מלמד אותו איך לשטוף.
כן, שהוא אומר לו לעמוד על ה... אתם רואים משהו שפספסתי מקום?
כן, שם אחת.
לא עושים ככה מחיקות, עושים מלמד.
רביד, כל אחד והדרך שלו, אתה לא צריך... נראה לי בסדר. אחר כך.
ראיתם שיש שטויות לקחת בקסמה לאש?
כן, שאומרים שהוא הרבה יותר חזק מיום.
בקסמה היה הרבה יותר חזק מיום, יש בו סמוי.
לא, אומרים שהוא עושה הזיות.
כן, אם אתה לוקח את זה פעם, זה כן.
עכשיו לקחתי, הייתי חולה שבוע, לקחתי...
תקופה שהייתי לוקח את סמוי כל יום.
למה?
הכל טוב. חקרתי כל הסק בו. רציתי לראות אם שלי מסתל.
כל יום.
הייתי ככה את הסמוי.
עזוב, אתה לא יודע גם איך הוא לקח.
בטח הוא לא לקח.
לקחתי שם. אבא שלי פעם אחת לקחתי גם ככה, הוא חושב שזה יום. הוא בא לך לעבודה, הוא פשוט לא חזר, הוא לא יודע מה קרה לו, הוא פשוט התקשר אליי בבית. פשוט אמר לי, אמא שלי שומעת, אני לא יודע מה קורה לי. ואז התחיל לחקור אותו וזה, ואז הוא סיפר, שאל אותו, תגיד, באיזה זה סגול, זה לא זה, ואז הוא אמר, מפגר, זה לילה. פשוט אבא שלי, אחי, לא יודע איך הוא חזר הביתה באותו יום. חקרתי את התיאוריה, אל תחקור את התיאוריה.
נפטר אחי.
Okay, let's start. So, one of the main principles of quantum mechanics is Heisenberg uncertainty principle. So, basically we have seen what is its origin. Basically, if we have two operators that commute, they can't be described by the same eigenfunction. And if I measure one, I have many possible results for the other, and vice versa. If they commute, they can be described by the same eigenfunctions, and therefore if I measure one, I know also the result for the other. Okay, now all we do here is quantify it with variance, give it a mathematical limit on the uncertainty. Okay, so we need two operators that we're interested in measuring. A and B. And we are at a given wave function, because the physical information is in this wave function. So what is the variance of A? As any definition of variance, A squared
the brackets will be square.
Okay, let's write it down explicitly. Well, syntax the squares here or here, it doesn't matter. Why is it true? So not necessarily real, but they're Hermitian. Remember, any physical operator is Hermitian, so the simple rule of thumb, you want to operate it on the right or on the left, you're welcome. Doesn't make any difference. So here I took the square and operated one to the left and one to the right. Why? You don't see yet, but is it legal? Yeah, definitely.
But that's legal for any operator, right? Because we have not performed the conjugation yet.
Well, I should have it would have been true if I put here dagger. Right, because this tells me operated to the right.
Right.
And here I'm operating one pair on the left. So for the scalar, it doesn't make any difference, of course, and physical measurement has to be real, so it doesn't matter at all. But here I should have written dagger, and I don't write dagger because it's Hermitian. Okay. That's just rewriting it in the Brian Cat language. It's not surprising that same way. Write it in a simple way. Okay, so the variance of A times the variance of B is larger than the commutation relation between them up to 1 over 2i. I'm a bit loose here in the way I present it because that's for a given psi. This gives me an operator, this is a number. Meaning, of course, is for a given psi. So what does it tell us? If I have two operators that don't commute, principle, I could measure one of them with certainty. But then I have maximal uncertainty in the second. I could decide I want to know a bit about the one and a bit about the other, but I have a limit.
So there you have used the Schwarzschild inequity, right?
In a moment you'll see that this is exactly what I did.
How do you get to the last line?
Excuse me?
No, understand the less likely? How do we get?
Okay, I'll prove it in a moment.
Ah, okay. I think you get it from here.
No. So, okay. I just wrote both definition one multiplied by that. And here is the Schwartz inequality. So, just a reminder, what is Schwartz inequality? And it's very intuitive. You look worried. The reason is very simple. This has to be always positive. This has to be always positive. This doesn't have to be always positive. Only after summation, then you square. So this is smaller than or equal to what appears on the left side. And there's also an additional term that if fr is just some linear multiplication of gr, then it's then and only then it's equal. Again, trivial. So, okay, so basically I can write down okay, what did I use here?
emission
In fact, that there are Hermitians, so I can pull it out of here and put it before the right side. Okay, so I have basically an operator A minus observation value of A times B minus observation value of B. Let me massage it a bit. except to bore you to this. Why did I do it?
To obtain the commutation relation.
But what's special? Is this a Hermitian operator?
No, the product.
No,
No.
because A times B is not necessarily a Hermitian operator. If you remember a couple or 3 lectures ago, we saw how to take a non-Hermitian operator and write it down as a combination of 2 Hermitian operators. So if I call this guy F, so F is Hermitian. And C is Hermitian if I add this I. So basically what's written above is the combination of
Where did I come from?
if you're in order for that to be Hermitian, when I want to change this minus to plus when I move it to the other side. So I do it by putting here an I, which after doing complex. If you want to see, we have checked it a couple or 3 lectures ago. We actually wrote how to take any multiplication of operators and turn it into a combination of 2 Hermitian operators. Here I didn't do anything beyond writing down what was written here with F and C. F and C are Hermitian, right? Therefore, the results that I'm getting here are real numbers. Throw it out. Why? Because it's still correct for greater than. I'm not sure. And now look a minute what appears in C. Okay, so I'm taking what's written here and writing down explicitly. Just wrote it explicitly. Minus, plus, plus, minus, plus, minus. What we intended to prove. For it to be equal, I need also that f will be equal. To be larger, so enough that it's larger than this. Questions? See unhappy faces, but I don't get questions. Okay, so looking at some more at home, and if you have questions, come back.
If it's equal, it means that the left side, psi f psi is 0, right?
That this guy is
Zero.
Is zero.
Just like the position operator and the momentum operator, their commutator is just have the imaginary part, so they can reach the equal, so they can equal to that.
Right. It depends on the specific operator. Now we will actually do it for a specific operator as you asked, position and momentum. So A will be the position operator, B will be the momentum operator. So I'll calculate the commutator. Okay, no matter what is the psi, if I have dou x times psi, I'll have once I'll get psi outside, and then I'll get psi, x times, let's do it.
Just the derivative of the product of functions.
Right, that's all. To understand it, always think about multiplying it here with psi.
It's like if we have a function of x in this multiplication, we get
Any function. At the beginning I told you you calculated for a specific psi, but for this commutation relation doesn't matter what's psi, you'll get the same. So that's it. Now you could have construct wave functions that are equal. I think I won't go into it. You can pick up any textbook and see how it's done. What the form would be, of course, a Gaussian. And intuitive, without going into mathematics, why a Gaussian? The Fourier transform of a Gaussian is a Gaussian. So whatever you find on what in delta x, you'll find with a different width on delta p.
why we scroll on the equation on the left.
Because there was a square somewhere beginning it. It's also a question of units. Delta x times delta p is units of h bar.
So I can write delta x, delta p bigger or equal to h bar divided by
Right. Okay, so the last topic that we'll do today is equations of motion. Sometimes people call it EOMs, and okay, in classical physics, what did I have? I have a position, for example, and I want to see how it develops with time. We can't ask this type of question in quantum mechanics. We can ask how probabilities develop with time. Now, instead of looking how the whole distribution develops with time, we'll look on averages. When we say usually equations of motion in quantum mechanics, we mean how the average of some physical quantity develops with time. So any physical quantity, again, I'm looking on some operator A, And I want to ask, how it develops, the average, how it develops with time. Wrote down the definitions. Nothing more, nothing less.
This is a generalization of the RFS theorem.
We saw already one example, which was the test. Now we're doing it in general. Like many things, we have some remnants of history in the ways that we're teaching quantum mechanics. Let's say the uncertainty principle delta x times delta p larger than half h bar. You saw it with energy and but all of these are basically two operators, A and B. So Ehrenfest is just a particular case of this equation. Now you can handle any physical quantity. Tell me what's A.
And it's easier this way, right, than to do the integrals.
Yeah, it is easier. Although proving it will do the integrals. What did I do here?
Just the function, all the three function is there.
I have here a multiplication of three functions, and I perform the derivative of a multiplication. So here's the first, third, and second. What is this guy?
Schrödinger equations.
The left hand of the Schrödinger equation. Again, The Hamiltonian is don't care its form. What is its mathematical property?
Intermission.
Hermitian. That's the only thing I need to know here. So basically what's written here is H times A. And what's written here is A times H. This is commutation. So I can rewrite everything that's written here. What have we learned from this exercise? Okay, first of all, a neat way to write down an equation of motion. The equation of motion of the average of A is the average of the commutation plus the average of the derivative of A.
It's just like classical mechanics, but we are
Right. Because the commutation and Poisson brackets are the same up to now. What else have we learned? We have learned something very important here. You want something that doesn't change with time, a quantity of the system that doesn't change with time.
make it commute with the
It
Hamiltonian.
must commute with the Hamiltonian. Well, first of all, it has to be time independent, but that's a trivial statement. If it changes with time, what do you expect? But even if it doesn't change with time, in order for it not to, its average not to change with time, the commutation relation should be zero. Actually, I could prove it from a completely different way. Someone has an idea?
Evolving the operator.
That's complicated. It's really a two-line trivial statement. It's based on something that we said before. If two operators commute, they have the same eigenvalues. Right? So if the Hamiltonian has no time dependency, so if I started with a wave function psi that is described by AE psi E sum over all E's, That's what we saw for Hamiltonians. It doesn't change. It doesn't depend on time explicitly. The probability of measuring some energy at time t. Right? So all this was regarding energy, and of course energy doesn't change with time. Not only doesn't the average or anything of the variant, any measurement has the same probability as function of time. Not surprising, but by now. But I know if H and A commute, has the same basis. So if I want to ask what is the probability of measuring some value of A, then it's because this is an expansion also in the basis of the operator where A doesn't change with time. Therefore, it's conserved. A is conserved. Nothing changes it. So we did it directly through an integral. We did it through our knowledge of linear algebra. Of course, they give the same result. So what we have here, we have conservation laws, meaning that it simply something is conserved if the commutation relation with the Hamiltonian is 0. Therefore, without knowing anything on what we will start in the next lecture, we can prove something that we know from classical physics. A free particle is the momentum conserved. On the couple of people, why? Because the Hamiltonian is and P with P square, of course. If I have some potential in my system, then momentum is not conserved. Why? Because there's no reason that P and V will commute. Generally, they don't commute.
Especially since V is a function of X, right?
Yes. So, in 20 seconds, I've proven that free particles conserve momentum. Particle in a box or a particle in a potential doesn't conserve momentum. Well, it makes sense. You go and hit yourself on a potential comeback. You don't conserve momentum. Nevertheless, energy, of course, is conserved because Hamilton always computes with Hamilton. Okay, so next lecture we're starting to do some examples of one-dimensional. As I'm doing in this course, we will try to put more emphasis on general properties of one-dimensional potentials than explicitly solving, although we will solve the example of a particle in a box and the harmonic oscillator. Both of them are important. Okay, so see you next week. Thank you.
למה בערך מוחלט האי כאילו אחד?
כאילו, זה כאילו כפר